Hello, I'm Ink. I will be solving today's second division kid first round 967, and I will try to explain what I'm doing. Problem A, make all equal. Cyclic array. Perform the following operation the most n minus 1 times. M is current size. You can choose any two adjacent elements. Previous one is not greater than the latter one. Delete exactly one of them. Find the minimum number of operations needed to make all elements equal. The left one should be smaller than the right one. It doesn't really make sense to remove equal elements, right? But we can delete either one. Is it true that we can just choose the element that will be left in the end? Like, let's say it's x, and then we can take all occurrences of x and then remove everything else. Well, that sounds correct. Like, how to remove everything that is smaller than x? We take the minimum element and then put the finger on it, and we can always remove it, right? Like it is always not greater than the next one. So this way we can remove everything that is smaller than x. How to remove everything that is bigger than x? Again, put a finger on the maximum element and look at the one to the left. It is not greater. This was the maximum. So we can always remove the maximum. So we can always remove the minimum, we can always remove the maximum. So if we want to remove everything that is not x, we will remove everything that is smaller than x by always removing the minimum one. And to remove everything that is greater than x, we will remove everything that will take maximum every time until everything is not greater than x. So the number of operations is just n minus maximum frequency, because we can choose any x. We will choose the one which occurs the most, so that we have to remove smallest number of elements. That is obviously optimal, because we have to remove, in every operation we just remove one element. Even if we remove the limitations on what should be true about that element, just in one operation you can remove one element. What is the minimum number of operations to make all the elements that are left equal? Well, you obviously choose the element that occurs the most and remove everything else. So that would be solution for problem A. Kinda cool. I guess it's not a good problem for people who guess solutions, because it is very easy to guess this answer. But I'm not one of those people, so for me, the proof is interesting, and it doesn't look like it will be the answer at the first glance. finding the maximum frequency just by putting all the elements in map and then printing n minus maximum frequency. Problem B, generate permutation. So we have an integer sequence, and initially it's just -1s, so the input is just n. Okay. Two typewriters. The first one writes letters from left to right with the pointer initially pointing to 1, and another one writes letters from right to left. Okay. Choose one of the typewriters and use it to perform the following operations until A becomes the permutation. Right number. Write the minimum positive integer that hasn't appeared in A to AI. We can do that only if it's -1, so it wasn't used before. Carriage return. Return the pointer to its initial position. Move pointer. Move the pointer to the next position. If we're using the first typewriter, we increase the pointer. If we use the second typewriter, we decrease the pointer. Okay. Your task is to construct any permutation of length n such that the minimum number of carriage return operations needed to make okay, so so there is a process with which Minsky can construct some permutation, and basically it just since we always write the minimum positive integer that hasn't appeared, it means that we put integers in the order 1, 2, 3, and so on, n. So our task is to construct a permutation such that if Minsky is using the first typewriter to do this, we can calculate the minimum number of carriage return operations to make this permutation, and that will be the score for the first typewriter. Then we can do the same, calculate the score for the second typewriter, and we want those two scores to be the same. Okay. Very hard to understand statement, but whatever. And we just want to construct the permutation. Okay, so well, okay, how to calculate the minimum number of carriage returns? Well, as I said, we put in the numbers in the order from 1 to 3 to n. And so, for example, if we using the first typewriter that goes left to right for free, but then basically, we're moving from left to right, and if we can put the number, let's put it, then we reach the end, and well, okay, jump back to the start and continue moving like that. So the number of times we will need to do this carriage return is the number of such values x, such that the position of x is on the right of position of x plus 1. Right? So, because after we print x, the pointer is here, we can move to the right, but the next number we should put is on the left, so we have to like do the carriage return and then go left to right from the start. So yeah, the number of carriage return operations for the first typewriter would be the number of such elements x that x plus 1 is to the left. Well, and for the second typewriter, it's the opposite. It's the number of such elements x that x plus 1 is on the right. For every like pair of x and x plus 1, they are either in the order x plus 1 or in the opposite. So it increases the score by 1 for exactly one of the typewriters. So for scores to be equal, we need like exactly half of those pairs to be in one order and the other half in the other order. So n must be odd. That is why for n equal to 2, we can see that it's -1. Amazing sample that doesn't explain anything except that like -1 happens. But yeah, like the solution should look something like put 1 in the middle and then jump left, right, left, right, left, right. Like putting somewhere in the left half, like so we'll put 1 in the middle, then for example even numbers on the left and odd numbers on the right. So like every time we switch the direction, so exactly half of movements will be to the left and the other half to the right. So for example, we can do like that. So for even n, it is impossible. Otherwise, it is possible. Well, actually, one of the ways to do it would be something like so I want to print like 2, 4, 6, and so on, like then reach the last even number, which will be n-1 because n is odd, and then jump to 1, and 3, 5, and so on. And there should be some simple way to do that, like yeah, just print like 2, 4, 6, but if that number x is greater than n, then subtract n from it. That should work. Two, 4, 1, 3, 5. I hope that is correct. From output a line of n integers, if it is possible, otherwise -1. Problems. Guess the tree. This is an interactive problem. There is a secret tree with n nodes. N is up to 1,000. We can use most 15 n queries. So like n log n plus some like n times constant, like 3, right? Or maybe like it's 1.5 n log n, but I doubt it. So like it's a good idea in such kind of problems where like you ask to find some objects in some number of queries, is to try to understand like what is the complexity of number of orders, number of queries that you allowed to make. You like it's not always that you can do it correctly before reading the problem. Like I haven't read the problem yet, but I would guess that it's like n log n plus 3n plus some constant number. Like that's what usually happens. Okay, well, what are the queries? We can ask A, B. I guess A and B are nodes, right? Like they're from 1 to n. Will tell you which node X minimizes the absolute value of distance from A to X minus distance from B to X, right? Distance is like number of edges. So alright, so for a pair of nodes, if the distance between A and B is even, so there is a middle vertex on the path, and like the minimum value of this thing is just 0. If more than one such node exists, we'll tell you the one that minimizes distance from A to X. That's important. So so we are comparing like distance AX minus distance BX, the absolute value of that, but we actually compare a pair of like this and then distance AX. And so in this case, this will be the node that is answered, because like it is on the middle of the path, so it obviously minimizes this thing, it's 0. There are other nodes that also minimize this distance. If we like look at this path and then in the node X we go away from the path and choose some node here, it will also like it is also equidistant from A and B, so this is 0, but the distance from A will be greater. So the one node that is equidistant from A and B and closest to A among those is this node in the middle of the path. If the distance is odd, this, then in the middle, like the middle of the path is this edge. So the minimum value of this thing will be 1, because it's impossible to be equidistant, like if we stay in the node, because, well, those two things are of different parities, so the minimum value will be 1. And the node we will get as an answer is this one, the one on the path that is like closest to the middle, but on the side of A. I mean, for this node, this value is 1. If we go out of the path in one of those two middle nodes, the absolute value of difference of distances will still be 1, but the node that minimizes, like among those that is closest to A, is this one. So okay, So our query will say like the middle of the path between A and B, and if the length of the path was odd, the one node that is like in the middle but close to A. And we need to restore the whole tree, right? What do we print? Print, yeah, n-1 edges. We have 15 times n queries. We can find some edge, right? Like if we start with like vertex 1 and some other vertex, let's say 2, like we will get as an answer like the middle of the path, then we can ask this to get the middle of the path, and so on, until we will get 1 as an answer. It means that like the node that we asked, the second one, is connected by an edge. Alright, so for this we will spend like log n queries. We will get this edge. What more we can do? We can actually restore this whole path. Like after we so there is a path from 1 to 2. We will find the first edge on this path, and then we can like do the same like from this point, like ask this vertex and 2, and then find like the next edge on the path, and so on. So for every such edge we will spend log n queries. The problem is that like, say we have found some part of the tree. If we node number 1 is somewhere here, we can then take a node that is unknown to us yet, like it is not in this restored part, and ask 1x, and let's say the path was something like this. So again, we can restore this whole path, paying like the length of this path times log number of queries, but we already know some part of the path. It would be very good if we can somehow understand fast where this vertex is, and then restore only this part that we don't know yet. Like, it would be cool to find the closest vertex. Maybe we don't really need it. Like, it would be okay if we just restore one edge in like log queries. So I guess we can do kind of binary search. Who would have guessed? So we start with like vertex 1 and x, do the query. Like the answer will be some node. Like let's say it's here. If it is not in our restored tree, we say, okay, we can jump to like 1 and this node. The distance between them was divided by 2. And like it is still true that the node 1 is in the known part and this node in the unknown part. Then we do the query and the answer is somewhere here. We're like, okay, then we can replace node 1 with this node. Again, the distance will be divided by 2, rounded up, but it's fine. And so, like after log queries, so basically we always maintain invariant that from the 2 nodes that we are currently considering, one is in known part of the tree and the other one is in unknown part. So we find their middle. If it is in known part, we move like the left side of the binary search, but like the known node. If it is if the middle one is unknown, we move the unknown. After at most log n queries, the distance between the nodes will be 1, and we will get just like one of them as the answer. And at that point we understand, okay, so we have those 2 nodes. One is in known part, the other one in unknown part. The distance between them is exactly 1, so they're connected by an edge. We then like remember this edge and say, okay, like this node now is in the known part, and repeat that n minus 1 times. So that's just n log n queries, like we do actually n minus 1 binary searches. Cute binary search problem. So every time we need to choose some node that is known, we can just always take node 1, and in the beginning we will initialize just the node 1 is known. All the other nodes are unknown, and so we know 0 edges. So for the known node we can always take the node 1. For the unknown node, we need to take some unknown node. Here the limitations are small, so we can do it with a linear check every time. If we wanted to have a faster solution, we could store a set of all unknown nodes, for example, or actually one thing that would work good enough is to try to take a random node until we find one that is unknown. Like on average, it would be just n log n queries. Like n log n tries to take a random node in total for one test, because like if we have k unknown nodes, then the number of tries on average would be n divided by k, and then we sum it up over all k from like n minus 1 to 1, and that's all of n log n. So we need to n-1 times. We're starting with node 1 and some other nodes that should be unknown. So normal thing to do would be to write while known u in ++, and that's how we find an unknown node in linear time. But another way to do it that should be good enough is to write while known, choose some random nodes. And that is actually faster on average. So now we are doing binary search. We do query vu, and if the answer is v, like we can write or the answer is u, but since we choose which one is node A and node B, and like, so when the distance between them is 1, we should always get back the first one we put there. And if the distance is strictly greater than 1, then we should get one of the nodes in the middle of the path. They should not be equal to any of those. So technically, like, it should be okay to just remove this part. But like, it kind of makes more sense to do it this way. So if the return node is one of them, then there is an edge between them, and we have found what we wanted. We can also like put here some asserts, like we want to have the first of them known and the second of them unknown. And that should be always true. And when we break here, it means that between v and u there is an edge, and v is known, u is unknown. So we will put the edge between them in the answer, and say that u is known now. Okay, if we did not break, then we have a node in the middle of the path now. If it is known, then we will make v equal to it, so it is still known but u is still unknown, and if w is unknown, then u will become it. That's it. Just need to print the answer. Does he print any bullshit like after the answer? No. Great. That's great. That's the correct way to do an interactive problem. Alright, problem D. Longest max min subsequence. Have an integer sequence S be the set of all possible non-empty subsequences of A without duplicate elements. Okay. Your goal is to find the longest sequence in S. If there are multiple of them, find the one that minimizes lexicographical order after multiplying terms at odd positions by -1. Fuck. Okay, the longest sequence in S is obviously we need to take one occurrence of every number that we have in the sequence. So if there are multiple of them, like we need to choose like occurrences correctly. So we want to find the one that minimizes lexicographical order after multiplying terms at odd positions by -1. Odd positions. Odd positions of the sequence. Okay. So 2, 3, 1 and 3, 2, 1. Yeah, right. So since in this sequence we have numbers 1, 2, and 3, we need to take one occurrence of each one to have the longest subsequence without duplicate elements. So we have to take this one and this two, but for threes we have two choices. So if we take the first one, the result will be 3, 2, 1. If we take the second one, it will be 2, 3, 1. So those are the longest options. And we choose 3 to 1 because, yeah, after we multiply first, third, and so on by -1, get lexicographically smaller. Okay, so like the first element should be maximum, the second minimum, the third maximum, the fourth minimum, and so on. Alright. Well, that kind of sounds easy. Like, maybe not. Okay, like how to do it in some complexity. So since we are caring about lexicographical order, we first need to make like the first element the best possible. I'm not saying maximum minimum because like some of them want to be maximum, some of them want to be minimums because of that like, multiplying by -1. So the first one should be maximum. And like it doesn't matter what happens afterwards. Like if we can make the current element better while leaving all the previous like, as is, and there is a way to continue the sequence, it is better than like making the current element worse, but then like it will be very good on the suffix. It doesn't matter. We want to make the first element the best, then the second element the best, and the third, and so on. So we will construct the answer like, left to right greedily. We need to choose the best element for every position. So what are the criteria? How do we check that like the next element can be equal to x? Well, since it should be like a subsequence, actually when we so we have already constructed some prefix, we can imagine that we like move a pointer on the sequence, and we need to encounter all the elements that we have already chosen in order. And it doesn't make sense to take not the first possible occurrence for every element, because, well, we want the pointer to be as much to the left as possible, so we have more freedom later. So for the first element that we have chosen, we will take just the first occurrence. But you can still imagine that we're taking a pointer and moving it to the right. Then, like after finding the first element, the first occurrence of the first element, we cannot go back in the array, so we will continue moving that pointer, and we want to find like the closest on the right occurrence of the second element. Then when we find it, we want to find the closest to the right of that one occurrence of the third element, and so on. How to check if like the current prefix that we constructed is valid? Well, we will find like this greedily, like by moving pointers, what is the occurrence of the last element we have chosen. So the pointer is here, and now to the right of this pointer we need to choose like all other elements that exist, but that their order is not really important for us right now. I mean, it will be important in the future, but right now we just need to check if there exists at least one order. So we forget about lexicographically minimizing anything. We just need to check that for every element that we have not yet taken, there is at least one occurrence there. So obviously for those elements, we want to take the last occurrence. So for every element, we will store like the positions of all occurrences, and also like the last occurrence is very important for us. So for all elements that are not that have not been chosen yet, we want to make sure that the last occurrence will be after everything that we have chosen. Okay, I guess like hence not enough here. So here is our array, and we are constructing the answer one element at a time. So we have like current answer, which is some numbers are already chosen. We now want to choose the next one. So for these chosen numbers, we have found their like leftmost possible occurrence in the array. So here we have B1. Then we want to find the leftmost occurrence of B2, but to the right of this one. So here is B2 somewhere. Even if we had B2 here, it doesn't matter. Like we can only move to the right. So we will find some pointers, and here is the pointer to the last current element. So these key elements we already have, they're all distinct. We have some other numbers that are present in the array, but we have not taken any occurrence yet. So we have some like, non-used for now elements. There are m of them, and k plus m is just the number of distinct elements that we have in the array. So for all those non-used elements, we know that this choice of prefix was okay. It is possible to continue. So all those elements, they have last occurrence somewhere to the right of this position. Maybe they had occurrences before, it doesn't matter for us. Maybe they have more than one occurrence here. It might be good, but like what is important for us is that all the last occurrences are here. So where will be the next chosen element? Well, I state that it must be somewhere here, like obviously after the previous chosen, but not after the leftmost of those like last position of unused elements. Why is that? Well, because if it's somewhere here, after this leftmost, it means that it surely can't be equal to this element, because then it wouldn't be its last occurrence. But that means that if we take this element to be the next one, well, it's bad, because we will not be able to take any occurrence of this element anymore, but we must do so. So the next element we take should be somewhere from this segment. The last element included, because like if we take it, we don't need to take it anymore. So yeah, the last element included. This one is not included. So it looks like we will need some data structures to do this. Maybe there are solutions without data structures, like without hard data structures, I mean. But like it looks like the simplest way to implement like exactly what I'm saying is to like maintain the set of non-used, not yet used elements, maintain the set of their last positions so that we can find the smallest of them fast. We will also like maintain a pointer on the last chosen element. So now we know this pointer, so we know the left border of our available elements. We know this position because it's the minimum in the set that we are storing. So we know this segment. Now what? Now on this segment, we want to choose either a minimum or a maximum element among those that are not yet used, because in our sequence they should all be different. So we need some kind of like a query on segment, either for minimum or maximum, with some special requirements additional. But like after let's say that we find like either minimum, maximum, whatever we want element, then I say like that's what we want, because like as I said before, we're doing this greedily. We want to choose the next element greedily to be the best, considering that we have already fixed what was before that element, and it doesn't matter what will happen after. If something can happen, if we can like in a valid way continue to build this answer, then this is good. Lexicographically means exactly that. So like, when the problem asks you to like choose the lexicographically minimum option, like you must do it greedily left to right. Like there is no other option. Like, that's like exactly the meaning of the word lexicographically. Like you want to make the first element the best, then the second, then the third, then the fourth, considering that all the previous choices are fixed and all the later choices are less important than the current one. Okay, so we find like what is the best value here, and like choosing any element from the segment is okay. Like let's say that we have chosen like some x and its last occurrence was here. Okay, we will remove this element from the set. It's still good. It's still true that all the last occurrences of unused for now elements are to the right of the current pointer. So that's fine. So we have chosen the best element here. There can be several occurrences of that element on the segment. We want to choose the leftmost one. We can either like put it in the segment tree, or we can just move this pointer until we find the closest occurrence of the element that we know we want. We know that it is somewhere on that segment. We want the first one, and the total number of like increments to the pointer is linear, so it's fine. We can do it in like stupid way. Just increment the pointer until we find the correct element. All right, so that's all great. That sounds like a solution, except for the part like we need to understand what is that magical data structure that will allow us to well, obviously maximum and minimum are the same, just like we'll have two copies of the data structure. So let's say we want to find the maximum element on the segment. Like it should appear on the segment, but it is not one of the already used ones. So to do that, we will just do the following. We will use a regular segment tree on maximum. But when we understand that we want to use some element x, we will go through all the occurrences of x and like turn them off. For example, set like -1 there, so that we do not consider those elements to be a good choice anymore. So when we do the query on this segment, like some of the elements are already -1s, it means that they're already used, they're not interesting for us. So among all the elements that are not -1s, so they're positive, we will choose the maximum one. And that is what we want. That would be the answer. So that is it. Like the total number of operations in the segment tree will be just linear of n, because like we can turn off every position at most once. So yeah, the total number of queries to the segment tree is linear. Total number of moving of the pointer is linear, and that's it. That's the solution. New example, yeah. As I said, the examples are bad, and like I would assume that if I were preparing a second division code first round, I would not be allowed to make examples that do not provide an example, actually. Like it's okay to like try to hide the answer, but you need to provide at least a way like to understand what does the participant need to print. And like in the example that we had in problem B, it's just number one for the case when it is possible, and then like impossible when it's impossible, -1. So you don't really get the picture of like how do you print this permutation. And I think like a lot of permutations would be good. I guess all except the increasing one and the decreasing one. So it's not like it's giving a lot of information away. The case with n equal to 3. So I don't really understand why the decision was made to not give it in the sample in the first place. Okay, whatever. Let's go back to problem D. Need to implement that. No, actually. Okay. Yeah, okay, so I have a segment tree. I want to use segment tree on max. But like I also need a segment tree on minimum. So to use the one on maximum, I will multiply all the elements by -1. But that means that like I said that I will use -1 as a element that like doesn't exist, but in the segment tree that is actually on minimum, where I multiplied all the elements by -1, like my actual elements are negative. So I will need to use something smaller as an like value that doesn't exist. So let's choose something like this. So like it's -infinity here. And so I want to have what is I want to have two segment trees, one for max, one for min. For every element, I want to store the positions. And also I need a set of all the elements that are not yet used, sorted by the position of the last occurrence. I can just put last occurrence because like when I have the last occurrence, I can look at the array and understand what was the element. So the elements are up to n, which is great. Thank you for that. Like it is not really needed, like you can compress the coordinates yourself, but it is nice to have them small so that like I can just clear up to n and not be worried about compressing the coordinates. No, not this, for what? So if I have such elements, I need to insert the last occurrence in the set. Great. So now I need to like populate the segment trees. Okay, now while I haven't found all the elements, I also need like the pointer to the last used position before everything is -1, like before the start of the array, because I will start using like from the next position. Okay, like this while is okay, but I guess it's better to make it like 4. The stop condition is still this, but I need to know the number of the iteration, or at least like I need to know the parity of the iteration, because on the like first, third, fifth, and so on iterations, or like in zero indexation, it will be on the even iterations. I need to take the maximum element, and on odd iterations, I will need to take the minimum element, which is just great, right? All right, so left border is ++1, right border is the first element in the set. This border is inclusive, so I'm adding one more. Now if the iteration is even, I want the maximum element, otherwise I want the minimum element. So here I want the maximum element on how does it call? Get. Okay. Maximums start in the first segment tree. So yeah, that's what I want. And here I want minimum in the same segment, but it is start with minus sign, so to get the element I will multiply by -1 back. Let's check that it's correct element. Okay, now I want to put it in the answer, and I actually need to do all the changes that I said that I will do. So for example, I need to find the next occurrence of this element. So I'm doing +++, and while a of pos is not x, doing plus plus plus. Great. We can also like assert that pos is smaller than r. And I need to remove it from the set. So static arrays for val of x back. And I need to turn off all the elements in the segment trees, like for all the positions. That's why I'm storing them. For all the positions, I need to like set point in the segment tree, point p set to -inf, and the same for the second segment tree. That's it. Really? Okay. So I will need to print like the size of static and spin, the number of distinct elements. Yeah, all of that looks correct. Okay, now we can move on to the last problem, but it is supposed to be like much harder. So it has two subtasks. The first one is like problem D, but the second one is that much harder. Okay, deterministic heap, easy version. The easy version of the problem's difference is the definition of deterministic max heap, time limit and constraints on NT. Interesting. So the definition is different. Well, maybe it's slightly different. We'll see. But maybe like if the definitions are different, maybe they're just two different problems with like difficulty comparable to D. Interesting. Okay. Consider a perfect binary tree. Yeah, so the usual how binary heap works. Okay. Each node has a value assigned to it. Define the operation pop as follows. So we started the root, repeat the following process until v is leaf. Among the children, choose the one with the larger value. If the values are equal, you can choose any of them. And then you like assign that value to the value of the root, but move the. Okay, so you pop the value from the root, and you like move up. Okay, so that's how it usually works in binary heap. Sign -1. So we like go to leaf and then sign -1. Okay. It says that the pop operation is deterministic if there is a unique way to do such operation. So at any step there shouldn't be like two sums with equal values. Okay. That's exactly what they say. Okay. Binary tree is called max heap if for every vertex the value in the node is at least like greater or equal to the values in sans. Max heap is deterministic if the pop operation is deterministic to the heap when we do it for the first time. Okay, and here we will have the first and the second time. Okay. Initially, all the values are zeros. The goal is to count the number of different deterministic max heaps produced by applying the following operation at exactly k times. Choose an integer v, and for every vertex x on the path between 1 and v, add 1 to ax. So we are adding on the vertical path from root to some nodes. So heaps are considered different if there is a node which has different values in the heaps. Okay, so we're counting not the number of ways to do exactly k operations. We're counting the number of different heaps. But okay, that just means that the root of the heap has value exactly k. We start with zeros, then k times we choose some node and add 1 on the path from root to this node. So the root will have exactly k, obviously, but then the fact that it is a heap will guarantee that there is a way to make those operations, right? Like, it is easy to calculate how many times. No, wait. No. Actually, the number in every node must be at least like greater or equal than the sum of values in the sans, right? Like for it to be a max heap, we just ask it to be greater or equal than the values. But if we construct a heap like this, like for every node, for every internal node, it is true that basically the value in that node will be the sum of values in the sans plus the number of times we applied the operation to that node. And so like the total number of operations should be exactly k. So that is the value in the root, but in every node, in every internal node, we can apply the operations in leaves. So in every node, the number of times we apply the operation must be non-negative, obviously. So the value in the node must be at least the sum of values in the sans, because of like how we build the values. But we count the number of heaps that can be constructed in that way, and that are deterministic, not the number of sequences of operations. Okay, that's probably important. Since the answer may be large, printed model P. Okay, so in this problem, n and k up to 500, p is big and prime, and sum of n, sum of k doesn't exist 500. And in this problem, just the first pop should be deterministic. In the hard version, n is smaller, but deterministic for the first and the second time. Well, yeah, because we care about larger number of nodes, I guess. All right. Okay, so oh, n is the height, so like 2 to the power of n is insanely a lot. But okay, like since we have a perfect binary tree, like all the nodes look the same on the same height. So well, the solution should be something like dp from a vertex, from the height and the value in the root, like the value in the current vertex. And I guess there will be like different. So we either care about this subtree being unique, or like pop going to the subtree being unique, or we don't. So okay, how to calculate the answer? Like let's say that this is tree of height some h, and here I want to have the value x. Then I know that the values in my two sons, like their sum is at most x. And let's say that like the first pop that we will do goes through this vertex. Okay, but that means that y should be not equal to z. Otherwise, it is not deterministic. So this should hold, this should hold. And we will go only to the one that is bigger. Let's say that like, y is bigger than that, but we can like swap them if we want. Okay, so we need to choose y and z, that like their sum is at most x. Then this subtree will have height like h minus 1, and it should be like deterministic, because like the pop will go to the subtree, but in this subtree it doesn't matter. So we will calculate like two dynamic programmings. So a of like height and value is the number of ways to like populate the subtree such that in the root we have value x, the height is h, and like deterministic doesn't matter. Come on, matter. And bhx, again, the number of ways to populate the heap of height h, and the root contains number x, but like deterministic does matter. So I said how we update b. So like b hx is like the sum over ways to choose y greater than z such that their sum is at most x, and b h minus 1 y, because like in this subtree it does matter, like the pop that we are doing, but in the other subtree it doesn't matter. But actually we need to multiply that by 2 because we can swap the sums. To update a, well, it's kind of similar but simpler, because if it doesn't matter for the whole subtree, it surely doesn't matter for sums, so we will have like kind of the same formula, sum over the ways to choose y and z such that their sum is at most x. Now we don't care that they're different, we don't care like which one of them is bigger, because we will always use value a. So it's h minus 1 y times a h minus 1 z. Okay, so in the stupidest way, like this is up to n, this is up to k, and this is up to like x square. So it will be like nk cube, but it should be clear that we can do the transitions for all x's at the same time. Like we can iterate over y and z, and then we need to add that value to all x's that are at least their sum. Well, we can just put it just in their sum and then like calculate prefix sums on that. So that will be of nk square, right? For every h we do k square operations. That should be good enough for the first problem. I think I should implement that, because like the second problem is like kind of a different problem, because the definition is different. Like it has some similarities, but we'll need to think more about like how first and second pop operations like, go together. So I have template for non-const modular arithmetic. So if n is equal to 1, the tree has just one node. So like that's just one leaf. So I'm starting my DP with height equal to 1 and then reach n. So if I only have one leaf and I know that I need to put X here, independent of whether I care about pop operation here or don't, there is exactly one heap that satisfies all the conditions, because like there are no other nodes. I know that I need to put X here, so yeah, it's all good. Whatever. So now iterating over height. So the GPA, which is just the number of trees, just iterating over all pairs x and y such that their sum is up to k, doing the update, but then we need to like calculate prefix sums. For the other DP, one of the subtrees should be strictly smaller than the other one. Their sum is still up to k. But now I need to like multiply it by 2 because I can swap the order of sums, which one is big and which one isn't. And again, calculate the prefix sums. Okay, I guess I need to use 64-bit. I mean, it's like 500 cube. Shouldn't be that much, but better be safe. Alright, so that should be the easy version. In the hard version, like I guess we'll have more dynamics. It's a bit weird that n is just up to 100. Like in the easy version, the complexity was like nk squared, and I don't see how like we can remove the k squared part. I mean, it is optimizable with like FFT, but the model is bad and k is up to 500. I don't think that FFT is faster than n square. So it can be n square, k square. That would be too much, I think. Not sure. Even on 64-bit, it's second. That's insane. So I guess it wouldn't pass on 32-bit system, whatever. Okay, so problem E2. So why does it matter to check the first and the second pop? Well, because after the first pop the values change, and also like we had those like two dynamics exactly because like in the first one we don't care about any pops, and the second one we care about the one pop that will go to the subtree. Now like it can be true that several pops will go to the one subtree. Also, like now the values will go up after the first pop, and then we will apply a second pop. So yeah, that seems much much more complex. Well, let's see what will happen. So okay, the first pop still should be deterministic. So we like if we know the state of the tree in the beginning, we also know the state of the tree after the first pop. So okay, in the beginning we had like A1 here, then A2, A3. The first pop must be deterministic, therefore we know that they're not equal, and without loss of generality we can say that this one is bigger. So we will just draw like what will happen, what is the state of the tree after the first pop, so we can like see how the second pop will look like. So after the first pop, well, we can say that the first pop just goes to the left subtree always, and for example just multiply by 2 to the power of n minus 1, I guess, because we can always like switch the subtrees, but we can always say that it goes to the left. Okay, so so here we had like A4, A5, and we know that A4 is strictly greater. Then we have A8, A9, and the left one should be strictly greater, and so on. In the end, we'll have like a 2 to the power of n minus 1 and a 2 to the power of n minus 1 plus 1, and this one is strictly greater. It's actually interesting that it's strictly greater. Oh no. If they would be close, then it will be like raise up 2 times, but no, okay, doesn't matter. Okay. So after the first pop, what happens? This element like goes here, so all of this will move up. So we'll have A2, 3, A4, A5, 8. A16 and so on. So what will happen with the second pop? With the second pop, several times we will go in the left direction, but then there will be a first time when we go right, or maybe there won't be, and we will just reach again the same leaf. Well, that shouldn't happen, right? Like in that leaf now -1 is written. So if we reach the vertex just one higher than that, we will go right then. So okay, there will be the first time when we go right, and after that, it's very simple. Like it didn't matter that the first pop happened. So in this sub-tree, it's just basically the dynamic B that we calculated. Right? So what is important is like what happens here. So why did we go left, 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 and then right? It's because this number is greater than this one. This number is greater than this one. But then here we have gone right, so the left one was strictly smaller than the right one. And then like it doesn't matter anymore. So okay, we need to calculate the number of ways to choose numbers, I guess like the ones that are drawn in this picture. Maybe A17 also. Yeah, probably. Like here we have A16 and A17. We know that this one is bigger. And so like here is A17, A32, but this is not important anymore. So like so here we have just a heap. Like we know of which height, we know what's in root. Anything else, anything that is lower is not important. But well, we are choosing the left heap to be like exactly correct. Let's use this. So like this thing is just a heap with this number in root, and we know what's the height. Okay, whatever. This thing is a heap of known height. We know what's in the root, but also we care that the first pop there is deterministic. So from here we're just choosing B. From here we're just choosing A. All right. For all those other trees which we don't visit neither in the first pop nor in the second one, like once we have chosen what is in the root, it's just a heap of known height, known number in the root. So we just taken the calculated dynamic A. So here also A. This one is different. This one, like on the second pop, we will go there, and like that second pop will continue in that subtree as if it was the first pop. So this one is actually dynamic B. All right, and now we need to choose all those numbers, all the numbers that are like drawn here, such that it is consistent with the choices that we made. So for every number, it should be at least the sum of its sums. And also, like, all the inequalities that are written here should be true. So like we have A2 is strictly greater than A3, A4 is strictly greater than A5, A8 is strictly greater than A9, A16 is strictly greater than A17, but also A4 is strictly greater than A3, which actually, like, this is kind of redundant. We know that this number is at least A4 plus A5. So if A4 is greater than A3, obviously this is greater. So A8 is greater than A5, so this is also kind of redundant. But A9 is greater than A16. So A8 was greater than A9, and it is not redundant. But A9 is greater than A16, which is greater than A17, which is interesting. Okay, so it looks like we should just like go from top, like go down this thing. And like, if we have reached this place, let's say I know what value is written here and here, but I haven't yet chosen the number here because I know that it should be smaller than A8, like the left sum here. So I need to kind of choose them together. So like this one is fixed, this one is fixed. Choosing this. And like after that, everything like strictly higher, like to the right, all of that is chosen, so I can like multiply by this pre-calculated A value for the given size. And also like at any moment I can try to stop and say that like, okay, I have reached this place where I will go right instead. And like choose the remaining numbers. Okay. So what do I need? I need to know the current height, clearly. Okay, now like it's harder to fit in the time. Like I guess like what I described just now is like, it's a valid solution, but it has complexity like uh, n times like I'm storing number here and here, so that's like k square, but also then the transition is to choose this number and this number. I guess I can just choose this number and then this is just bounded by like it should be strictly smaller than this and also strictly smaller than this, which should be true anyways, and also like the sum of these two should be bound by this, so um, yeah, it just bounded by some value, so I can pre-calculate like um, prefix sums of like those a values, so it will be just nk cube. That's not good enough. Um, 12 minutes, like there is no chance I can implement it, but I can try to find the solution. Although it's probably like not very hard to write if I come up with it, but probably don't have enough time to come up with it anyways. It still bothers me that like n made smaller, but not small enough to allow like for force power. Like I would understand if k was made smaller. Then like making k 5 times smaller will reduce this complexity like 125 times. So like actually this is already good if n is up to 500 and k is up to 100, but that's not the case. Why do I say that I need to store values in two nodes? Because like if I only store this one, I have to somehow choose this one. But also not store it. Okay. I guess I can store like this and this. That's still it's two values. Maybe I can make transitions faster. Okay, well, let's say that this is X, this is Y, this is Z. Like, if I'm storing like pair XY, I want to make transitions to pair YZ, but X is not that important. I mean, it is important in the sense that like it gives limitation on this value. Let's call it, I don't know, U. So, like, how many transitions there are? And like, what is the what is the coefficient I need to multiply the DP value when I do the transition? I need to multiply it by like the sum of like sum H, which is like this height, which I know, U, but the sum over U, like under some conditions. What are the conditions? Like U is smaller than Z, like that I know from here, and also Y plus U is not bigger than X. So the value with which I should update this YZ is sum over Z is sum over X, it is at least Y, it's XY multiplied by sum over U that is at most strictly smaller than Z, and Y plus U is at most X of some subsum. Like, yeah, this also has height, doesn't matter. So all of those has height somewhere. Maybe like it's -1 somewhere. Never mind. I mean, obviously those are different. So like it's +1. I should be able to calculate it faster, right? Maybe not. Unclear. I mean, I guess it kind of depends, like, which of those two limitations on u is stronger. So we basically have like u is smaller than minimum of z and x minus y plus 1. So this thingy only depends on this, and this thing only depends on this. So if we do those transitions separately, like depending on whether like which one of them is stronger. So if that is smaller than this, then this sum only depends on that. So let's say that we have like p of z, it's the prefix sum of this thing is z. Like for this guys, I need to do update with like x at least y plus z of cxy times p of z, and it like this coefficient doesn't depend on x anymore, so I can pre-calculate like suffix sums of those for fixed y with like different x's, and like for given pair yz I can make all of those transitions at once. And if this is not true, then like x will be between y and y plus z, and for those maybe strictly, never mind. For those this thing doesn't depend on z. So it only depends on x, so I can pre-calculate those values for x and y. Like for fixed x and y, I know this sum, and so I can like name this some other letter just from x and y, and then also calculate prefix sums of those and take the sum and segment in constant time. Okay, that should work. So let's just take the solution that is already written to calculate a and b, and then do all of that. That will still be nk squared. I don't understand, still don't understand why n is smaller, just because like we don't want TL to be very big. Like yeah, the constant factor of this solution is worse. Like I need to calculate more sums, more products, more stuff. Just there is more stuff, but with the same complexity. So I guess they reduced n to not have to like increase time limit a lot. I also didn't think like what will happen in the end, but I'm assuming it's kind of similar. Shouldn't be that big of a problem, but maybe it is. But like while I'm on this path, I think this works. Well, nice. This is like my kind of problem. Like I would prefer that in like a CPC style contest, obviously, because like basically it is solved on paper, and then you just need to write like 20 lines of formulas, like prefix sums of those, of this, and have arrays A, B, C, D, E, F, G. Yeah, but nice problem, I assume. If I mean, the solution is cool. Like you just understand what is going on, and then okay, I have like some polynomial solution. I know how to do it in like k to the fourth. Then we can do k to the third, and then by doing in 3 separate cases, we can like pre-calculate those prefix sums, these prefix sums, all of the prefix sums, and yeah, get it and update it in constant time in the end. It's my kind of problem, yeah. Thanks for watching. We can take a look at the results. That's impressive. Kevin didn't solve it. Maybe he just left. That's alright. Alright, thanks for watching. Bye.